Okay. So lab assignment is due today. I believe Cindy's going to bring the solution towards the end of the class for you to pick up. I did some soul searching about the presentations and the last day of classes. I think the best thing to do is just stick to the original plan. I'm going to skip the faculty retreat on May 5th, at least the portion in the morning. By people who did projects rather than just literature survey. At this point, I forget who's doing what. I think I think a lot of you are doing projects, but some are just doing pure literature surveys. So people who are doing projects, just actually let me just do a quick show of hands. Just about everybody here is doing projects, right? Yeah. You're doing a survey. And David, are you doing a survey or project? Okay, you're with that group. Okay. So, excuse me. So we'll just stick to that plan. We have about 2 hours. I think the only issue is with you, Casey, right? That's okay. You just hand in your PowerPoints together with your report.
Okay.
I mean, unless you can attend the Friday, May 5th class.
That might be possible.
Oh, it's possible.
Yeah,
Okay.
I'll be back by then.
Oh, if you're here, by all means. I just was under the impression you couldn't make it.
29th was the, I don't know when I'm coming in. Maybe it's in the
Okay. Okay. No, I didn't mean to exclude you. It's just that if you can't make it, that you can hand it in as part of the PowerPoint. Okay. Any questions? Yeah.
When is the report?
Whatever I said in the original handout, which was May 15th. Yeah. Yeah.
How long do you want for the presentation?
Well, basically, the algorithm we apply is we have about an hour and a half. We might go over because on Fridays there's no class right after this. I might also actually reserve a different room in Corey because then they have a LCD projector. If I change the room, I'll let you know ahead of time. But basically, I think there's about 10 projects, and there's about 90 minutes or so. So it's about 10 minutes per project. Something like that. Any other? And then there's some groups that have more than one student. Actually, at some point, I'd like you to let's do that, just so that I have an update. Since the last time I received your proposals, there were some changes in the groupings. Some students merged into one group, and I was going to say some split, but I don't think anybody split. So if you guys can, what's the best way of me figuring out exactly how many groups there are and how many projects? Why don't you just send me an email? I'll keep track of it. So each group, and please, no more than one person per group, because otherwise I'm going to get confused again. Okay, send an email to. Actually, Cindy, can we send that? No, just send it to me. That's fine. Make the subject line. Make it EE225B, because then when I go search among my 7,000 emails, I can, at the end of the day, I can figure out. If you just put EE225B in the subject line, then I can quickly locate it. It's because, yeah, I mean that, otherwise it's going to take me 5 hours to find all your emails, which is another big problem. Okay, subject line EE225B, tell me the number of people in your project and the title. Let me make an announcement here for people who come late. It's May 5th. As planned is the presentation day. 4 projects. Okay? And if you didn't completely get everything done by May 5th, and between May 5th and May 15th you got more done, that's fine. I don't expect your project to be in its final form on May 5th. Kind of an overview of what you've done and what you hope to accomplish by the 15th. Any other questions or comments? Okay. So today was yeah, and then pick up the solution on your way out. Pick up the draft solution. That's here. Questions, comments? Yeah. Yeah, why don't you CC Cindy as well? That's a good idea. And once we collect the title of the projects, then I'll come up with a schedule and I'll announce it. I'll try to come up with a schedule and then announce it so that, you know, okay, well, this group will go first, this group second, and the timing and stuff like that. Okay, any other questions? All right, so let me get going on today's lecture. So what we talked about last time was essentially variations of waveform coding. We talked about pulse code modulation, which is just simple idea of get the pixels, quantize it uniformly, and kind of just send the quantization bin, allocate bits to each quantization bin and send that over. Then we talked about delta modulation, where you essentially subtract successive pixels and quantize the you subtract the current pixel under consideration from the previous pixel that you encoded, but the quantized version of that, which the receiver has access to, subtract those two, you get an error, and then quantize that. It's not f of n minus f of n minus 1. It's not that what you quantize. Rather, it's f of n minus the quantized version of f of n minus 1, simply because the encoder and decoder need to maintain this loop. They have to maintain the same state. The encoder has to know, can only work with quantities for prediction. It can only work with quantities that the decoder has access to. And the decoder, unfortunately, only has access to the quantized version of the previously encoded pixels, not the actual uncompressed ones. So in any event, so that's how, if I were to show it on the camera, this was the guts of delta modulation from last time. Okay, this was PCM right here with Roberts noise. This was regular PCM. This is PCM with Roberts noise. This is delta modulation. And we ended last time's lecture with DPCM, differential pulse code modulation. And so just as a reminder to you guys, how it worked was you start with the pixels. Once again, you have some prediction for what f of n1 and n2, the pixel at location n1 and n2 is. This is the pixel you want to encode. You come up with some prediction, and that I deliberately don't tell you how it is. It could be linear, it could be nonlinear, it could be fancy, it could be any complicated function you ever dream of. And this prediction is a function of all the previously encoded pixels. And in this case, I've only written 3 of them, but it could be all of them, if that's what you want. you come up with the error, PCM here means you quantize that error, you get E hat. This E hat is what gets sent to the receiver. But meanwhile, at the transmitter, you want to keep track of what the receiver is doing. And so what do? You add E hat to that prediction, and you compute what the receiver would have computed, which is F hat of N1 and N2, the estimate, so that later on in all your predictions, you only use the values that the decoder has access to. Decoder and receiver are used interchangeably. So you only use the pixel values that the decoder has access to. So you store that in the bank of all the previously encoded pixels so that then you can use it later on for prediction of the next pixel and the next pixel. Is that concept more or less clear? Yep. Anybody? And for different kinds of data, you do different things. For example, if you come up with an autoregressive model for images, you can make a prediction which is a linear combination of these things, right? What Cindy is working on is she's working on compressing VLSI layouts, and VLSI layouts have very nice Manhattan geometry, straight horizontal edges and straight vertical edges. So then you build your predictor to match that kind of a data. The better you make your predictor and the more you utilize the knowledge of the domain that you're working in, the smaller the energy of this error is, and the closer f prime is to f, therefore the smaller the variance or the energy of this error signal is, and the smaller the energy of this signal is, the fewer bits you need to spend it to represent it with a given fidelity. Fidelity meaning distortion, mean square error. If I have a fixed mean square error in mind encoding this error signal, I would spend fewer bits in representing that if the variance of E is the smallest possible. So you want to make f prime to come as close as possible to f, and you can be as clever as you possibly want in the prediction process. And this is, by the way, true when we get to video coding, where the prediction box is predicting between successive frames. That's where the motion vectors come in. Anyway, the receiver is pretty straightforward. You get E hat, you add f prime to it, and f prime, because it was built off of a known prediction function of the previously encoded pixels. All those previously encoded pixels are available to the receiver. You add them up, and that's what the receiver displays as f hat of N1 and N2. So what are some variations? Before I get into the equations and tell you how we do the prediction, at least one example of the prediction, I want to talk about two things. What's some of the pitfalls of this system, and what are some variations of this system? So how about if we change prediction as a function of the region of the image that we're dealing with? Let's say with some regions of the image it's flat, some other regions it's more textury. You might say, well, let's just adapt the prediction. What would be the pitfall in doing that? Yeah, I mean, every time you adapt, you gain, but what do you lose? Well, you have to send extra bits to the receiver so that the receiver also knows you switch to a different prediction mode. Let's say the transmitter had 5 prediction modes and the receiver had 5 prediction modes, and you could choose, or 4, for example. So if the transmitter has access to the actual data, raw uncompressed data, so if the transmitter chooses the best prediction model, the problem with that approach is that you still have to send the overhead as to specifying which one of the 4 or 5 prediction models you're using. And we'll talk about that a little bit more now. So every time you do adaptations in all these compression techniques, you gain some, but you have to make sure that doesn't get offset by the extra overhead you have to send. And looking at these two loops, the transmitter loop and the receiver loop, what else could go wrong? Anybody? Suppose you're sending this thing over a wireless channel where the packets get lost, the packet gets dropped. So suppose one particular E hat of N1 and N2 was in a packet that, due to some channel conditions, got lost, and we weren't applying an end-to-end protocol like TCP. It was UDP, and let's say it was a low delay application. We didn't even have a chance to retransmit it, so boom, one of these guys is gone. That means the receiver can't build f hat of N1 and N2. What do you think happens? Yeah.
They get out of sync and it gets worse and worse.
That's exactly right. They get out of sync, and It actually depends on whether or not the receiver knows that that pixel is lost. Let's just, for the sake of simplicity, say it knows. If it doesn't know, then it really gets massacred. But let's just assume it does know that it didn't receive a particular E hat of N1 and N2. Yeah, it can't compute F hat, and it gets out of sync, and the error just propagates. And so for that reason, in almost all prediction-based schemes that are error-prone, that is likely for things to get lost, you have to have resync points where things get resynchronized in order to remove all these things. So of course there's error concealment techniques. If you read the image processing and video communication literature, there's error concealment techniques that, like for example, the receiver, in order to make sure that all hell doesn't break loose, it could, for example, use some other values of previously encoded f hats, f hat of n1 minus 1 and n2, for example, as estimate of f hat. Okay. So what I want you to understand is these are two very tight loops, and they're in sync with each other. So now what I want to talk about is what are some possibilities. Today I want to start with what are some possibilities in terms of coming up with a prediction box like this. Okay. And I'm going to talk about that just now. So the picture that for the sake of completeness for this system, let me just redraw the so we're talking about DPCM. Let me redraw the diagram from last time. So you start at f of n1 and n2, and you subtract from it your prediction, f prime of n1 and n2. Here is your quantization, and out comes E hat of n1 and n2. And this is what gets sent to the receiver. But locally at the transmitter, you still want to know what the receiver is doing. So you add up here this E hat with F prime in order to come up with F hat of N1 and N2. And this F prime signal here really is the output of some prediction box. And the prediction is based on previously encoded pixels. I'm just repeating that same diagram so that it's fresh in the new sheet. So it's F hat of N1 minus 1, comma N2, etc., etc. So having drawn that, so the question that we're going to start answering is, how do we do the prediction? Roll up, please. Great. A little bit more. Great. Okay. So how to predict? And the answer is, well, let's write down, let's say that we do what's called linear prediction. We write down f prime, the predicted value for pixel n1 and n2, as a linear combination of the previously encoded pixels. So we write down f prime of n1 and n2 is the double summation of k1 and k2, taking the values in some region of support r sub a of k1 and k2, times f hat of n1 minus k1, comma n2 minus k2. Okay. And so all you're saying is linearly combine these previously encoded pixels in order to come up with this prediction. So now the question is how to choose A. And this is where we ended last time's lecture. Well, we better we better choose A kind of in an optimal way. We better choose A, in such a way that we maximize something or minimize something. And one way to do that is, as I told you earlier, this is E of N1 and N2. The smaller the energy of this signal is, or the variance of this signal is in a statistical sense, the fewer bits we spend to represent it. So a nice thing to optimize is to minimize the energy of this signal or the variance of the signal. Okay, so a good thing to do, as I said, is minimize expected value of E squared of N1 and N2. That's what we want to do. And what is expected value of E of n1 and n2? Well, it's equal to expected value of E of n1 and n2 squared is equal to the expected value, and you can now write down the gigantic equation for E. Well, it's f minus f prime, but f prime is now this summation, so it's square of f of n1 and n2 minus f prime, and f prime is this double summation. A of k1 and k2, a of k1 and k2, f hat of n1 minus k1, and 2 minus k2. Okay, so that's what we want to minimize. And in general, this is because f and f hat are related in a nonlinear way through this quantizer up here and various other things that's going on in this system, that this is hard to minimize. Ideally, every time you're minimizing something, you want to end up with something quadratic. If you're minimizing with respect to some variable, in this case a, you want to have something that's quadratic in a, so that when you take the derivative of it, you get linear system of equations. You solve it with known techniques, and boom, you're done. This is not quadratic because this f and f hat are related in a nonlinear way. In particular, this is f hat. They're related through this quantizer, which is nonlinear. So what do? Well, we kludge our way. And the way you kludge your way, you say, well, you know, and ideally, if you're doing a good job of quantizing and if it's a really good compression system, f and f hat are very close to each other. Okay, so ideally, f is approximately equal to f hat. So I'm just going to shamelessly replace all these f hats here with f. And then I do get a quadratic system. So then I get E of expected value of E of n1 and n2 is just expected value of this thing squared, where this thing is just f minus a, and then f of n1 minus k1 and n2 minus k2. Okay, so I just shamelessly replace this f hat with f, and this is index for k1 and k2. And now what I have, this thing is really quadratic in a of k1 and k2. And in order to, so our goal is to minimize this with respect to a. So we want to minimize with respect to a's. So take derivative, set it equal to 0. And if we do that, then what we get is a linear system of equations. So then we can get a linear system of equations that we can use any technique we like. And the solution to that is given by the following. R sub f of L1 and L2 is equal to double summation of K1 comma K2 being a member of R sub A of K1 comma K2 times R sub f of L1 minus K1 comma L2 minus K2. Okay? Well, what is R sub f? Well, it's the we're assuming that f is a stationary random process. We're assuming that R sub f is the correlation function. So R sub f of n1 and n2 is the correlation function for the stationary random process f. Okay. So once again, we've not only in restoration problems but in compression, you've kind of come up with statistical models of your image, and you're assuming that it has, you know, is stationary, it has correlation function. And we've already bashed the stationarity assumption many times, but we keep coming back to it, and I mean, it's not strictly stationary, but you can still do some interesting things if you assume it's of that nature. Okay. So so you can, so how do you so if you come up with some models for your R sub f, for example, then you can come up with, so you assume some sort of R sub A, region of support, and then assume some sort of a R sub F, and then you can come up with A of K1s and K2s. Okay, and in particular, if I were to show figure 1030 in Eennlb's book, if you use, so this picture here, if you zoom in, shows the 3-bit per pixel quantization, DPCM quantization of the Leno picture with the signal to noise ratio of 16.6, where the values of A sub K of K1 and K2, I'll write it down in just a second, were obtained, are given as follows. So this 3 bits per pixel, I want you to compare kind of with, unfortunately again, Eennlb doesn't have a very good set of comparisons. Here he has a delta modulation picture with 2 bit per pixel. I'll switch to Gonzalez to give you some better feel of the different prediction methods and various other things. But for now, if you can kind of come back here, so I'll just write down figure 1030 in Eennlb. You assume A of 1 comma 0 is the same as A of 0 comma 1 is equal to 0.95. And that probably corresponds to a particular model. He doesn't even state it exactly or precisely what it is, but some model of R sub F. And then A of 1 comma 1 is minus 0.95. Now, as I said, a much cleaner example is a little bit more in detail is Gonzalez and Woods. He actually uses different prediction equations in order to come up with different images, and I'll show some of that too. I think it's a lot more insightful than what you have in Eennlb's book. So bottom line there is that here are some possible prediction equations. Okay. So you could say that f prime of n1 and n2 is, for example, just 0.97 of f of n1, comma n2 minus 1. Just a one-tap prediction model. You could say f prime of n1 and n2, another prediction model, is 1/2 of f of n1, comma n2 minus 1, plus 1/2 of f of n1 minus 1, comma n2. So we call that prediction model 1, prediction model 2. Then the third one, f prime of n1 and n2, is 3/4 of f of n1, comma n2 minus 1, plus 3/4 of f of n1 minus 1, comma n2, minus 1/2 of f of n1 minus 1, comma n2 minus 1. And notice in all these examples, we're summing up. We're making sure that the sum of the coefficients of these guys add up to 1, because if all the pixels are between 0 and 256 and the sum of the coefficients add up to 1, the predicted pixels also will have the same range. So we don't want to increase the energy of the signal or decrease it. So we call this prediction model 3. And finally, the fourth one is a little bit more complicated. It doesn't necessarily do better, but I'll write it down anyway. F prime of n1 and n2 is 0.97 f of n1, comma n2 minus 1 if delta H is smaller than delta V, and I'll tell you what these guys are in just a second. 0.97 f of n1 minus 1, comma n2 otherwise. And this is called model number 4, and delta H is defined as f of n1 minus 1, comma n2 minus f of n1 minus 1, comma n2 minus 1. And delta V is f of n1, comma 2 minus 1 minus f of n1 minus 1, comma n2 minus 1. So basically what this last thing is saying is that these two things, delta H and delta V, they basically denote the horizontal and vertical gradients at point n1 and n2. So this is the horizontal gradient, and this is the vertical gradient at n1 and n2. This is the vertical gradient. So if the horizontal gradient is smaller than the vertical gradient, then copy the pixel that's for this pixel, N1 and N2. You're copying the one from below. And in this case, you're copying the one from to the left. Okay. So this is copy from below. Essentially, this is copy, or 0.97, almost the same thing. Actually, yeah. And for the other case, copy from left. Okay. So here's some prediction schemes that people have been playing with, and let me show you the resulting. Let me now log in here, fire up the Internet Explorer, go to my web page, which has all this stuff. Chapter 8, yeah. Okay, and we want to go to figure 823. So okay. So if you switch back to the computer, so this is favorite picture that Gonzalez uses for all these examples. I don't know what he calls it. This is a 512 by 512 monochromatic image. And if you go to this page now, what you see is the prediction error that you obtain by using all these four predictors. And again, ideally you want your prediction error to look like what? Very low energy and white noise. You don't want to be able to discern any of the features of the original image in there. Because if you do, it means that you didn't decorrelate the pixels good enough, right? It means that there's correlation between the pixels that's left to be exploited. So on the upper left is scheme number 1, which if you switch back to here on the paper, it's just a linear thing, 0.97 so here I'm just saying copy the pixel from below, the previously encoded pixel, and that's my prediction. And as you can see in here, switch back to the camera, it kind of does terrible. Okay. Then if moving here is a two-tap filter. It's half of n1 comma n2 minus 1 plus half of n1 minus 1 comma n2. Does a little bit better than this, but still you can discern a lot of the features. This one is a three-tap filter, and you can see there's considerable less energy than these two. The variance of this signal is smaller than the other two. And this is the one with delta H and delta V with the horizontal and vertical. And I mean, I thought that this guy Gonzalez puts this example in because this is going to be much better than this, but in fact, you'll find out that they're not. And if I were to assign a mean square standard deviation of the prediction error, not the variance, but just the standard deviation, which is very closely related to variance, this image is 4.9, very high. This one is 3.7, slightly lower. This is 3.3, slightly lower. And this one is 4.1. So it didn't. This fourth one with the delta H and delta V, and look at the gradients for horizontal and look at the gradients for vertical, it didn't necessarily do better than the three-tap filter. So but the smallest amount of energy is this. Okay. So let's just any questions on this?
What's the significance of the 0.97? Like the other ones, the energy always added up to 1, or like...
Yeah, actually, I was thinking about that as I was writing it. You can just have 1. I don't think it makes any difference. I think, yeah. I don't think it makes any difference. So so let's just go one step further and try to combine this. Assume for just a second, now you have this prediction error, and so how do you end up quantizing it? So quantize and bit allocate. This is not the signal you send. Every pixel in these prediction error images now it still has an integer, right? In fact, you subtracted two images that are each one is between 0 and 256. The dynamic range, in fact, increased. It could be anywhere between plus 512 to all the way through. What could it be? What's the range? Minus 256 all the way to plus 512. So it's quite large. So we still have to do quantization to do. So what are some approaches for quantization and coding? And I realized I could have covered that last time, but we'll cover it now. So you can do non-uniform quantizers. And the way you do that, the optimal one is Lloyd Max. And we talked to some extent about Lloyd Max in last time's lecture. And so what does and Wei talked about it 2 lectures ago. What does Lloyd Max do? It says, I have a random variable with a given PDF, probability distribution function, and I wanted to quantize that to n levels. Find me the quantization bin boundaries and the reconstruction levels for each of those so that I minimize mean square error. So let me just remind you one more time of Lloyd Max. It's the optimum non-uniform quantizer. Basically, it says assume a PDF for your random variable. We want to quantize to n levels. Then what is the decision boundaries and what is the reconstruction levels? Right? You all remember that from last time. So this is min, this is max, and this is some probability distribution function. So you put it in some numerical algorithm and say, okay, these are the decision boundaries, D1, D2, D3, and for this quantization bin, the optimum reconstruction level is here. For this one, it's here, and I'm exaggerating here, right? For this one, it's here, and for this one, it's all the way to the end, right? So think of Lloyd Max quantizer as a nonlinear box that takes the probability distribution as input and n as input and produces this D1, D2, D3, which are decision boundaries, and I call these R1, R2, R3, R4 as quantization levels. And so if I apply that, so now suppose that I assume that these prediction errors we need to know what the probability distribution for these prediction errors are to begin with. So how do you do that? You take few images. The images have tons of pixels. You plot their histogram, and that gives you an idea what the distribution are. And what is the distribution of prediction error pixels? I don't expect you to know it, so I just tell you it's Laplacian, right? So assuming that the PDF of the prediction error is Laplacian, then I can quantize it to I don't know, 2 levels, 4 levels, 8 levels. And if I were to look at Eennlb's book, that he had I don't know again if Wei showed that or not, but he has a table that tells you what the so there's tables that tell you for a given kind of a PDF, for example, Gaussian, Laplacian, uniform, I don't know, Rayleigh, all these distributions with unit variance. All these all have parameters. You have to tell what the variance of it. It tells you it solved the Lloyd Max quantization, and it tells you the optimal DIs and RIs, right? So if I were to go back to this, look at the table 10.1 in Eennlb book, we can see what they are here. If you zoom in, please. Okay, great. So like for uniform, Gaussian and Laplacian. So uniform, if I have 1 bit, that's 2 levels. If I have 2 bits, I have 4 levels. If I have 3 bits, it's 8. If 4, it's 16. This is how this table works. So for uniform distribution, okay, yeah. So for uniform, the reconstruction level, and here we're assuming that for uniform it's between -1 and +1, right? The reconstruction levels therefore make sense. It's -half and +half, and the decision boundaries are -1, 0, and 1. And if you go to 2 levels, then these are the reconstruction levels and the uniform. Did Wei go through this table two lectures ago? Okay. And this is for level 6. Anyway, so if you do all of those things, then you can go back here and see the DPCM results using 1 pixel, using 1 bit per pixel, 2 bits per pixel, and 3 bits per pixel on this image that he doesn't give it a name. And again, if you look at the book, I don't know if it comes on this cameras on the TV screen, but this is blurry. This is quite blurry, with the edges are not really sharp, and as you go to 2 bits and 3 bits, it becomes better and better. Now, let me explain to you what these other pictures are. So, and the way to do that, let's come back to the paper here. What if the probability distribution of the random variable you're dealing with is not unit variance? I mean, these tables I just showed you for Laplacian and Gaussian, they were constructed for unit variance. What if they're not? What if the variance was 5 or 10 or 20? It's very simple. You just scale these decision boundaries and these reconstruction levels, and multiply them by whatever number they are. So it turns out that you can make this DPCM adaptive by, for example, doing the following thing. Look at 16 by 16 block, and you compute its variance, right? Well, if it is 1, then good. Just go to the table that has Laplacian for 1. But you can categorize or classify the variance of the 16 by 16 blocks into like 4 classes, okay? And so essentially you have 4 scaled quantizers, right? And where the scale factor in this case is 0.5, 1, 1.75, and 2.5, right? So you can pick. So ideally, what you would, if you wanted to do Lloyd-Max quantization, you compute the variance and then go to the ideal PDF distribution for that Laplacian. But then if you do that, you have to send the variance values of each block across, and that's expensive. That's complete adaptation. So in order not to spend a lot of bits on specifying the variance, what you do is you say, okay, I'm going to compromise. I'm going to assume my variance falls into one of these 4 groups, and therefore I scale my unit variance Laplacian assumption by these 4 values, and I classify each of my 16 by 16 blocks into one of these 4 classes, and therefore I'm doing now what's called adaptive quantization compared to DPCM. And as you can see, the quality of the picture is quite a bit improved. And if you don't see that, this picture is even better. This is the error, the difference between, so let me go back here. So this is the, let's just call it the Lena, well, what should we call this lady? The lady image. She reminds me of Queen Elizabeth. It's her birthday today, but if you call her lady, just anyway. This woman picture. This is 1 bit per pixel. This is 2 bits per pixel, and this is 3 bits per pixel. So this is adaptive quantization. Now that I have to specify for each 16 by 16 block, I have to send 2 additional bits because I have to tell which one of the 4 classes of variance I fall into. So it's 2 bits divided by 16 pixel. Now I have 1/8, which is 0.125 bits per pixel extra of overhead. So this is 1.125, this is 2.125, and this is 3.125. Better yet, look at the error. After you've quantized and coded that, this is the error that you get with 1 bit per pixel with no adaptation. This is 1.125 with with adaptation. This is with 2, 2.125, 3. The left columns are all adaptation. The right column is all adaptation. The left columns are non-adaptation. 1 bit, 2 bit, 3 bits, 1.125, 2.125, and 3.15. So as you can see, you go down here, the error gets reduced, and this is how in compression papers you present your results. You don't, the same problem we have, by the way, showing things through the screen is just as bad when you publish your papers. You can submit electronically your paper, but then by the time it gets on paper, on a real hard copy paper, it's all gone. All the things you observed in real life in your lab just evaporate. So a better thing to show is these error signals that kind of completely shows what the picture is all about. And if you're not happy with that, you look at the actual mean square error values and the different prediction equations. This is kind of the table you get, right? So if you use that simple prediction equation, these are the mean square error values you get for 2-level, 4-level, and 8-level Lloyd max quantizer. And you can see when you move to adaptive, it's dramatically increased by a factor of 4 or so. A much lower mean square error. Again, if you go down this way, you also see that for non-adaptive, the energy keeps decreasing, except for that this is the delta H, delta V thing, which never did anything useful, and I don't even know why he has that example. The same thing here, the same thing here, the same thing almost here, here, and here. But so as you go down, the mean square error for the prediction error goes down. And as you go from here, non-adaptive to adaptive, it also goes down. So these are kind of in jive with our intuition as to how DPCM should work. Okay? So let me just write down here. So 2 bits of overhead to do the classification, just for the sake of having these notes. And so 2 bits over 16 by 16 pixels, 0.125 bits of overhead. Okay. Any questions in this whole scheme? Okay. So I'm going to continue now. We're done with waveform coding. Okay, it's not really used. It's the simplest of techniques, but you use it in situations where you don't have much compute power, or it's one of the earliest the image compression techniques designed. So the next thing in our list of what to code besides waveform. So we did waveform coding so far. Done. The next thing is transform coding. Okay, and how many of you can tell me why we do transform coding, or or what transform coding is? Anybody? Any transforms you guys are seen in your life? Does anybody know what transform is?
It can be in frequency domain, DC, TDF.
Yeah.
It can be wavelet.
Yeah. Okay, excellent. So the main...
Before that, can we ask you a question?
Yeah, sure.
Like you said, overhead is 2 over 16. Shouldn't it be 2 over 16 square?
Yeah, I wrote down 16 square, but I said 2 over 16. So 2 bits over 16 times 16.
So that won't be 0.125.
Or is it 8 by 8? Sorry. Let me just quickly look. That was a good point. It's not 16 by 16 blocks. It's 4 by 4 blocks. Sorry. All right, thank you. Okay. So variance 1, variance 2, variance 3, and variance 4. Thank you. Okay, so how does transform coding work? Well, you start with your signal, and you take the transform of it, and then you quantize the transform coefficients. And the transform could be DCT, DFT, etc. And then you do code word assignment. This is the bit allocation. So after you do quantization, which could be uniform or non-uniform, you then have to assign bits into each of the quantization bins. So bit allocation, this could be Hoffman, arithmetic, anything you like. And then at the other end, you receive this, and you do inverse transform, and then inverse entropy code. This is bit allocation, or what's called entropy coding. You do inverse entropy coding. For example, if you did Huffman, you have to undo your Huffman code. And then you do inverse quantization, and then you do inverse transform. You just inverse all the steps you took in order to spit out f hat. Now, if you didn't do any quantization, then this would be a lossless scheme. But because you quantize, you're introducing errors. So my first question is, why do we do transform coding? What's the number one motivation for doing it? Why, I mean, waveform coding looked pretty nice, right? What do we hope to gain?
Well, because some transforms they compact energy.
Exactly. Exactly.
A lot of coefficients are close to zero.
Exactly. Because the transforms do two things that we're interested in. Number one, if you take an 8x8 or 8x8 blocks and you take its transform, you get 64 numbers. A large number of those 64 coefficients are very close to zero and can be discarded. And we've already seen that at the beginning of the semester when we took DFT of images and we threw away, I don't know, 99% of the coefficients. You take inverse transform and boom, it still looks like the original. So this is called the compaction property. They compact the energy of the signal in the space domain into very, very few coefficients. So ideally, you're interested in finding transforms that have very good compaction properties. And number two, so that's good, Sergey. What's the number two reason? You might know it also. Of the coefficients that didn't become zero, what can we say about those? They are highly uncorrelated. The pixel domain, the problem with the darn pixels is that they're very correlated, and we have to find these A coefficients to uncorrelate them, and sometimes we're good, sometimes we're bad. It's just, you know, shooting in the dark almost, hit and miss. But the transform, if you have a good transform, statistically, the coefficients of the transforms are uncorrelated with each other. So let me write this down. So Y transforms, there's two things. Number one, they achieve energy compaction, okay, in a small number of coefficients. And number two, they reduce or eliminates, if there's a fantastic transform, eliminate, I can't spell today, the correlation between transform coefficients. So knowing the fifth transform coefficient doesn't tell me anything about the sixth one. So there's nothing for me to exploit statistically. I don't have to do, if I'm in transform now, I don't have to do prediction anymore. I can toss that out, which is a big headache. I mean, you saw the different prediction scheme, etc. So no need for prediction. Okay. So what is another constraint? What are some constraints that we have to consider in doing transforms? First of all, it has to be invertible. If you do a transform that you can't invert, then you send these coefficients across, and the receiver, the decoder, can't reproduce the original image. So transform must be invertible. And secondly, computationally, it has to be tractable. It shouldn't be too compute intensive that it kills us. And this was, again, this was an issue like in the 60s where there was not too much compute power. It disappeared in the 80s because now we got fancy computers on our desk. It's reappearing in the 2000s because why? You need to do it on a low power cell phone, portable device without burning a hole in your pocket, right? So before I go and talk about, show you the basis functions for some of the popular transforms, I like to talk about the optimal transform, which is KLT. How many of you have heard of it or seen it in your other classes? Okay, is it in 225A? Did Michael Gasper cover it? Okay, so how did you guys know about it? Some other class or something? Just heard about it. So the optimum transform, I'll spend a few minutes over it. So the optimum from a statistical point of view is KLT. Karhunen. Oh boy, now I have to spell that. Oh, okay. It's K-R-H-U-N-E-N, Love transform. Do we have any Finnish people in the class? I think Sergey comes closest, but you're not Finnish, right? Actually, I used to have some Finnish classmates when I was studying in UK, and the biggest insult you can do to them is to tell them they're Russians. They get so mad. They say, oh, you're just an extension of Russia. You're a colony of Russia. Oh, they get furious mad. Anyway. Well, they all speak Russian. I mean, this was in between 78 and 80, before the Berlin Wall fell, and before, when the Cold War was going on. You probably weren't even born at that time, but it's very true. They're right next to Russia, and they teach Russian as their second language. Anyway, so Karhunen Love transform. So Karhunen, as you can see, is a Finnish guy. And how does this thing work? Well, first of all, let me tell you what properties it achieves. Number one, it's optimal in a sense that the coefficients are completely uncorrelated. And that's exactly what we wanted, right? And number two, on average, in a statistical sense, the first m coefficients have more energy, for any m, have more energy than any other transform. In other words, you start with a bunch of pixels here, you pass it through KLT, and out comes a bunch of coefficients, right? So if you have 1,000 pixels, you come up with 1,000 coefficients, but it comes up with rank order these coefficients, C1, C2, all the way C1000. And if I draw the line anywhere, if I pick the first 3 coefficients, they have more energy than any other first highest value, highest magnitude coefficients from any other transform. If I pick the first 5 coefficients, they have more energy in them percentage-wise. See, these are all energy-preserving transforms. In other words, the sum over f of n1 and n2 squared, that's very important to say, is the sum over f of k1 comma k2 squared. So the energy is preserved, right? But so if I added up c1 squared plus c2 squared all the way to c1000 squared for all the transforms, dct, klt, dwt, dht, anything, the sum squared of all of them is the same number. This is preserved because this number, they're all equal to this quantity. But the good thing about this KL transform is that if you pick the top 3, percentage-wise, it has the highest percentage of energy in that top 3 than any other transform. If you pick the top 3 of DCT or DFT or any other ones. If you pick the top 5, for any m, the top m coefficients contains the largest percentage of energies compared to all the other transforms. And that's what's beautiful about it. And like many other things in signal processing information theory, when you first are presented with this, you say, oh, God, I'm in 6th heaven, Where is it? Let's use it. What is it? Let me see what it is. And unfortunately, we have to pour cold water, just like I told you, the brick wall filter doesn't really exist. This thing doesn't really work very well either. Why? I'll tell you why, because as soon as I tell you what it is. So assuming, so how do you build KLT? Assuming f of n1 and n2 belongs to a stationary random process, and you can already see the beginnings of the troubles, right? As soon as you assume it's a stationary random process, you have to assume it's our correlation function. Then with a covariance function, which is defined as k sub f of n1, comma n2, column L1, comma L2, which is defined by expected value of x of n1, comma n2 minus x bar of n1, comma n2, the whole thing, times x of L1 and L2 minus x bar of L1, comma L2. So this is the covariance function for this random process. Then you have to come up with the basis functions for this transform. So assuming all of these things, then the basis function for this transform, which is defined as a of n1, comma n2, column k1, comma k2, satisfies the following. It satisfies the following eigenequations. And again, I won't have time to show why this is true, but here's the eigenequation that it satisfies. Essentially, lambda is the eigenvalue, lambda of k1 and k2 times the basis function a of n1, comma n2, column k1, comma k2, and a lot of these things are complicated because there's two dimensions, is the same as the summation from k1 equals 0 to n1 minus 1 and k2 equals 0 and 2 minus 1 of k sub f, which is the correlation function here, or covariance function, of n1, n2, k1, k2 times the a guy, a of L1, comma L2, comma k1, comma k2. Okay? So a is the eigenfunction, or the eigenvector. I mean, in the discrete case, you can talk about eigenvector instead of eigenfunction. So a is the eigenvector of this kf guy, the covariance function. Okay, that's called the. Actually, I forgot what it's called, but this is essentially satisfying the eigenequation of this nature. Have you seen something like this in 225A? Like whitening filters and stuff like that. Yeah? Anybody? Have you seen an equation like this in 225A? I don't think so. Anyway, so the basis function. So what I mean, what was all of these? And so why do I care about the basis function? Well, because the basis function is what I use to compute my KLT coefficients. So let's just wrap up this whole discussion in a sense that my coefficients, which are f of k1 and k2 for KLT, having said all of these things, is just a projection of my signal on top of these basis functions. It's the double summation of f of n1 and n2, where n1 and n2 of a of n1, comma n2, k1, comma k2. So what's the sum? What does all of this thing amount to? You start with this signal f. You assume it belongs to some stationary random process class which has this kind of covariance function. You have to compute that, or know it, or evaluate it, or find it somehow, somewhere. Then once you know that, then you can solve this equation to find the basis functions, the a guys. And once you know a, then you can project your signal f on a to get your KLT coefficients. Okay, now that we've described it, why is this process full of bad things? Well, commutations aren't stationary. Even if you just overlook that, computing this guy f is hell. And even if you just say, okay, you know what I'll do? In fact, Roz Picard, who was my classmate at MIT, who is now a professor at MIT, she had an entire summer job at Bell Labs, where what she did is she would evaluate K sub f, this kernel function, for every image, and come up with an image adaptive basis function. Because then for that image, these coefficients are completely uncorrelated, da 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 da. But what's the problem with that approach? You have to send the A guys, the basis functions, to the receiver, and that already kills the entire compression scheme. So okay, she spent the summer proving that. Then you can think about it and say, okay, well that was a bad approach. Let's just not do that. Let's just get a class of images, compute K sub f for all of them at once, come up with some sort of universal basis functions that works with a lot of images, and that's what we use. And to some extent, that's kind of what DCT is all about. So let me explain what I mean by that. So if you so in practice, so KLT in practice is just hell. Actually, I shouldn't write hell on paper. Difficult. Okay. There's a permanent record of this stuff. Goes on the web pages. It actually is being used for a course, many courses in China. Okay, it is. So if I assume, it's true, they came and asked for permission. So if I assume that my image is a Markov has a Markov model. Okay, and what do I mean by the image having a Markov model? That means the correlation function, expected value of f of n1 and n2 times f of n1 minus I, comma n2 minus j is equal to some number, sigma squared, times rho sub v I times rho sub h j. That's what that assumes, right? Where rho sub h is the horizontal correlation coefficient, and rho sub v is the vertical correlation coefficient. In any event, if you assume something like that, then you can show, well, in this case, let's just assume that these two things are equal to each other, and let's just call them rho. Okay? Then we can show that as rho tends to 1, then fortunately KLT approaches to DCT, which is fantastic. Okay? And that brings us to the next page. If you can roll up, please. What is DCT? Well, there's 4 types of DCT. But the type 2, which is the one we're most interested in, is given by the following equation. It's discrete cosine transform. And it's given by S of K1 and K2 is equal to so the DCT coefficients is equal to the square root of 4 over n squared of C of K1 times C of K2 times the double summation of n1, n2 ranging from 0 to n minus 1, both of them, of the signal S of n1 and n2. And I apologize for now switching to the S signal, but that's okay. Cosine of 2 things. Oh, I'm not going to have space there. So cosine of pi, 2 pi, n1 plus 1 times k1 over 2n, and then cosine of 2 pi, n2 plus 1, k2 over 2n. So this is the forward DCT transform. And you might say, well, what are these C guides? Well, C of k is defined as have 1 over square root of 2. If k is equal to 0, it's 1 otherwise. Okay? So this is how you take DCT of type 2 for Worry coefficient. And what I'm going to do on Wednesday's lecture, I'm going to explain how DCT is related to DFT. Okay? But for now, what I like to do is show you the basis functions, these cosine guys, pictorially, so you can see so you can see how they look like. Okay, so here we go. If you can go figure 830. Yeah. So this is a discrete cosine basis for n equals 4. Okay. Where so you have 16 functions, as you would expect. This one is the DC term. This one is the highest frequency. This one you have vertical bars. This one you have horizontal bars. And this is what you get when you're dealing with a 4x4. If you have a 4x4 blocks, then they have 16 basis functions. These are the 16 DCT basis functions that you end up getting. Okay. Actually, I'm telling you, I have a typo here. You know what my typo is? I just discovered it, and it's in these notes as well. This is pi times 2n plus 1. The 2 is here. 2n plus 2. 2n 2 plus 1. 2n 1 plus 1. Okay? I was wondering what's happening. Okay, so anyway, there's 4 kinds of DCTs, and I'll get into the details of it a little bit more. And just for comparison, this is the Walsh-Hadamard transform, and I will write down the expression for it and everything next time. But let me just go to this picture and show you what happens if you apply approximating that woman picture with Fourier transform is up here, Hadamard transform is here, and cosine transform is here. Okay? Why are you laughing? They're all the same, right? Let me see if I can find something better. Okay, this is much better. Yeah. Okay. So as a matter of practice, well, you know what? I think I'm going to stop here because there's too much. Once I start doing that, then I'm going to skip. I'm never going to be able to finish this argument. So let's pick up this DCT discussion, and we talk about the block sizes. We talk about energy compaction, how it compares to Walsh-Hadamard, and we talk about threshold coding, zonal. Yeah, there's too much to just try to ramp up today. Okay.
Before we all run away, let me make 2 short announcements. Is that okay?
Yeah, sure.
First of all, there's going to be a free pizza lunch at the
And if you don't want to meet Swiss people, what do you do then?
Well, you
Then you come to the office hours.
Just grab pizza on the way. And
Just
it's at Olsen at Shadow above Eckbauer. That's what I heard. Never been there before.
Eddie Bowers, by the way, is out of business, so don't look for that. It's at Alston and Shattuck. That's a good thing to say. Yes.
And that's the first thing. And the second is tomorrow is Cal Day, and at iHouse we are having a spring fest. And dozens of companies from all over the world are going to present their crazy stuff. And Switzerland is going to do some very interesting things. I heard they are going to
Will there be chocolate?
There will be chocolate. I told them, make sure you bring
Okay.
chocolate. And they found sponsors for the chocolate, and they are going to bring tons of chocolates. So come and have a look if you have time.
All right.
Excellent. Thank you. By the way, how many of you went to that Wednesday talk at 4?
We had class at 5.
Oh, and how was it? It was interesting? And what do you think, Cindy? How was it? Ah, okay. Don't forget to pick up the solutions on your way out.
Professor, I have a question. So if I'm just doing that literature survey, do I just turn the report on the 16th?
Yeah, yeah,
Okay.
yeah. Actually, just to apply some uniformity
Right,
to everyone, why don't you attach your PowerPoint?
Okay.
Okay.
Sure.
How is it going?
It's good, yeah. I've been reading a lot of papers.
Are you primarily looking at the spectrum issue? Oh, no, there was one